Okay, now I've got a metal rod here. You can't see the whole thing, but it's about, somewhat over a meter long. And I'm going to just wiggle it back and forth here. It's fairly easy to wiggle. I'm going to take a roll of wire here, put it up near my hand. It's not much harder to wiggle. Matter of fact, I can't really tell the difference between having the wire, having this thing on the rod or not. Now, if I move out halfway to the end, okay, so here it is. Here's halfway and here's the other end, okay? About halfway to the end, it's a little harder to wiggle, okay? Now, if I move it out all the way to the end and wiggle it back and forth, she's all the way to the end, okay, now. And it's much harder to wiggle. And you can measure it. You can measure the torque and everything. Um, but it's not just torque. It's you're trying to accelerate mass at some distance. And if you've had physics, you know about moment of inertia and all that stuff. And that's what we're going to learn to calculate by integration. Moment of inertia of various types of solid. So here's a rod. Now, if the rod had no mass at all, because the rod itself had some resistance to being wiggled, right? And you probably didn't even double the difficulty by putting that roll of wire halfway out. But by the time you got to the end, it was a lot harder. Okay. So try to pivot the thing here. And you put the mass, we'll just say we attach a mass here and assume a light rod where the difficulty wiggling the rod is negligible, much lighter than the one we use. Okay. Maybe it'd be a wood rod that long, be lighter than the metal rod. And you can think in terms of an ideal rod where the mass here is a whole lot bigger than the mass of the rod. Okay. If it's a distance r, difficulty wiggling is proportional to mr squared. Okay. Also, the difficulty of just holding it up. Is proportional to mr. Difficulty of holding it up is torque. And we could say the torque is mr squared. Now that's not really quite the case because it's really mg times r squared because its torque is, I said mr squared, it's mr. Torque is a force times a moment arm, okay? Now I'm not going to get into the physics of it, but if you've had physics or taking physics or are going to take physics, you'll learn about that, okay? Here, Moment of inertia, call it I equals mr squared. Okay. And what you're trying to do there is not just hold it up, you're trying to accelerate it. Difficulty of accelerating that thing, the torque applied at the pivot. Okay. You don't need to understand the physics of it. But now, let's say I've got this rod with a bunch of masses. Okay. So now, same thing, same rod, but just a bunch of masses. Now I'm going to spend a lot of time drawing masses that I really rather not do. Okay. So you got a mass M1 at position R1. Mass M2 at position Rn and so forth. Mass M sub n at position R sub n. So your total moment of inertia is the sum of the moments of inertia of the individual masses. Okay. And I say it's approximately equal to because what's R1, R2, or Rn? Those masses might be this wide, or you measure in your R. Somewhere between here and here. Well, I'm going to say we're going to measure it at a sample point. Okay. And I could even do an Ri star. So you can have R1 star, R2 star, up to Rn star. You understand that we're leading up to forming an integral, right? Because these are the kind of sums that you allow to approach an integral. Total torque is approximately sum from I equals 1 to n of mi r sub I star. That makes sense? This takes account of how difficult it is to wiggle each mass, and you add them up. So I add a bunch of masses on there, you're going to have to wiggle them all. Okay? This is what it takes to just hold it up stationary. Let's say that you have a triangular object. I'm going to pivot the thing about this end. It's got some length L, and it's got a width here that we'll call H. Then if we pose an x-axis here, and we take some interval of that x-axis, now I just used x for my variable, and I'm going to change it to r, just to be consistent with what I wrote over here so you don't have to worry about the difference. Interval delta r at r star. If this represents a flat piece of stuff, okay, just a flat laminar triangle, density I'll just indicate by rho and assume it's a constant density. What's density? It's what you multiply, in this case, by area. And I should be using a sigma instead of a rho. Matter of fact, let me just go ahead and do that. It's a density of area, and we usually call that sigma, lowercase sigma. Okay, it's kind of like an O with a stem on it, moving out mostly to the right. Okay, laminar density, sigma. What's the moment of inertia? Corresponding to this interval. See what you get. Give you a minute to think on that. Now come around and look what you're thinking, so I know what to say next. Okay, now I see people trying to do an integral, okay? Well, we're going to do an integral. That's what we're leading up to, but we're just asking about one interval, and that's what you need to focus on. If you can figure out what happens in the typical interval, then figuring out what to integrate is relatively simple, okay? And figuring out what to integrate if you don't know what's happening on just a single arbitrary interval is next to impossible, okay? I mean, there's some things that I've integrated enough that I kind of know what the integral is going to be. But if I want to be sure that I know what I think I know, I better start with an increment, even though I know darn well what to integrate here. Okay? At least when I think it through from the increment to make sure that I'm not messing up. Okay? As an engineer, I want to double check everything I do. I want to be sure everything I do is precise. I recommend that you develop that focus on precision in every course you take, including this one, okay? So, that aside, to get the moment of inertia, what do you have to have? You have to have mass and a distance from your pivot, okay? So, I would start by figuring out what the mass in this region is. Then before you can figure out what the mass is, you better figure out what the area is so you know what to multiply by the density. Okay? So I would start by finding the area corresponding to this interval. Then I'd multiply it by the density to find the mass. And then I'd multiply it by r star squared. So let's start by finding the mass. As I asked, some people had to think a little bit. Okay, now. Okay, I recommended that you find the area corresponding to that interval. But I didn't see on anybody's paper until I started hinting that maybe you'd better show that area in your sketch. Okay, what's the area corresponding to this interval? It would be this area right here. Okay, what is the dimensions? It's a trapezoid, but we're going to calculate the dimensions as if it was a rectangle whose length is whatever it is at r star. Okay? So what would the dimensions of the approximating rectangle be? Okay, I'm going to draw this picture. Here's our approximate region. It's tapering. It's of width delta L, as we should know. I'm going to leave that implicit. And then we have an Ri star, which is somewhere. Okay? It's not even Ri star, it's just R star. So this blue line is at R star, and our approximating rectangle will then be there's the same thing, but approximating rectangle is going to just be this, where this dimension is the width of this triangle at R star. So what is that width? See if you can get it, write out the expression for that width and then take it on to area and mass. I don't like to keep harping on our educational system, but it's a simple proportionality you should be able to do in middle school. Okay? But you've probably never seen it. I'm going to write it out for you. This is L. This is H. This distance is R star. What's this distance? That should instantly click. But I don't see evidence of instant clicking. So you really need to pay some attention to simple middle school geometry. Okay? It's easy, but it's a bit of understanding and knowledge that you really need again and again. So kind of make note of this. When it clicks, make sure it stays clicked. Okay, after letting people think and still kind of staring, say, do you see two similar triangles within this picture? And do you know what to do with similar triangles? Can you draw the two similar triangles? What do I mean by similar triangles? I mean triangles with the same angles. I'm not seeing much. Got a similar triangle. Well, the whole triangle is right here. That's one of your two similar triangles. Where's the other one? It's right here. And I'll draw the second one in blue. These are similar triangles. They have the same angle because this line is perpendicular to what's implicitly an axis, right? Okay. And that axis runs all the way through. So this thing is perpendicular to the axis. This thing is perpendicular to the axis. And I realized that you might not be able to see the whole thing on screen. So there we are. Maybe even a little further. Something's going to fall off the other side and break something. But there we go. Okay. We know the dimensions of this one. This is H by L. Do we know any of the dimensions of this one? Well, I'm just have to do this. This should instantly click. Okay. You really need to tutor yourself on uses of similar triangles in proportionality. It's just clear that our schools aren't doing it. And you need it. You simply need it to think. So this is what? Well, this dimension is, surprisingly, well, if this is R star, then this dimension is L minus R star. Okay? This is something you should have done 100 times. I'm serious. I'm pretty sure I did this sort of thing 100 times before I took Algebra 1. Okay? We didn't even take geometry until after we took Algebra 1. And I'm pretty sure that the rest of the world has done this 100 times. The rest of the educated world, including most third world countries. Okay? Again, to have the thinking skills you're going to need to compete, you need to remedy some of this. You don't have time right now. You're too busy with your projects. Okay? Find time sometime to learn what was supposed to have been taught in the curriculum before you got here. All right. And please don't take offense at that. I'm not saying you're an inferior human being, only if you don't remedy it. And then I'll probably never see you again because you're dying in a gut or something. Just, no, not that bad, but it's hyperbole. Look that word up if you don't understand what it means. Taking a small truth and blowing it up into something ridiculous, okay? You're probably going to die in bed before long. Not in the gutter. Seriously, stay alive and learn this stuff, and you'll have a better life all along, okay? That's what I'm really about here. All right, so you got L minus R squared H, and this distance here, which is what we really want, which is kind of abusing notation. I'm going to call this H star. So here's a small rectangle. Here's L minus R star. What we're trying to find is the area of this region. To find the area of this region, we got to know how long this is. We'll call this H star because it is h measured at r star. Well, then we can write the proportionality h star over L minus R star equals h over L and solve for h star. And the proportionality we really have is L minus R star divided by L. L minus R star divided by L looks like it's about 2/3. Looks like L minus R star, which is this, it's about 2/3, 0.6, 0.7, whatever, of L. That's what this fraction is, okay? And this is going to be the same fraction of this, okay? The H star is going to be the same fraction of H. And I really recommend that even for this course, you just ponder this until you understand it completely, until it's like something you were born knowing, okay? It's that important. All right. Well, we can now say that this area here is H times L minus R star over L multiplied by delta L. Okay. So that, what's your expression for the mass? You multiply the mass is just this expression multiplied by sigma. Your approximate total mass is the sum I equals 1 to n of sigma times H times L minus R sub I star over L times delta L sub I. Now, what I've done is I've jumped from one increment. I say I've got it for any old increment. Now, specifically, I divide this up into n increments and add them all up. I'm not going to do all the notation for that because I've done it in other contexts. You should be able to fill that in. Okay? You have to understand every detail of this, to understand what an integral is telling you, and to understand how to figure out what to integrate. Okay? You start with an increment. and you figure out what the contribution of that increment to the total happens to be, whether you're in 2 dimensions or 3 dimensions or 48 dimensions. Okay. And this approaches the integral Okay, now I've used delta L, which isn't consistent. They call this a delta R, right? I mean, it is a delta in the same dimension as L, that I was just kind of focusing on something besides my notation. But it's delta R. And you need to be careful of that just because I'm not. Don't let that distract you. Okay? So we get sigma H times L minus R over L. PR from what to what? Well, our interval basically goes from 0 to L. That's kind of implicit. And it makes sense to have our position at the pivot be 0 and then go to the end. And I wanted the moment of inertia. So I was just doing a first moment because I'm talking about all kinds of other stuff. Here's your area, here's your mass, and I left something out. And I'm going to have to insert. I mean, we're doing moment of inertia. Moment of inertia is mr squared. What I'm calculating here is just the mass. Okay. Well, that's what I said, total mass. So I don't have to do, I wasn't doing moment of inertia. For a minute there, I lost track of that fact because my brain's a little bit scrambled these days. It'll either get worse or it'll get better. It's allergy season. Who knows where it's going to end up. I apologize for that little bit of confusion. But yes, here's our mass. That's a simple integral. So the moment of inertia it's the sum of your mr squareds, right? More specifically, sum of your delta m sub I, r sub I star squared. Okay. Now this is the sum of your m sub I sum of your delta m sub I, if you can read that. All you got to do to get the moment of inertia is multiply by your r sub I squared. It equals something which approaches then the integral from 0 to L of the same thing. You got to integrate this expression to get your mass. but you throw in r squared. In rectangular coordinates, your r might coincide with x, okay? But on the other hand, well, we'll do another example here in a second to show what I'm going to say. Now, this integral is no more difficult than this integral, or just a little bit algebraically more. You're going to have to multiply r squared by L minus r, so you're going to have RL minus R cubed, right? And then everything else is a constant that just comes out of the integral. So just integrating r squared minus, LR squared minus R cubed. That's very easy. Just do the algebra, okay? Let me digress to one thing that I wanted to say about your tests. In regrading the tests, the problem where I had you convert the coordinates from one system to another, turns out that the only place you would have seen that is in a section that wasn't assigned before the test. Now, you should have seen that in pre-calculus. You should have seen it in calculus. You should know it, just like you should know similar triangles, okay? Theoretically, but I'm not going to hold you responsible for that on a test where you hadn't seen it within the last several months, okay? So I'm probably going to omit that problem except for the one person that got it right, okay? Or maybe if it doesn't help, I won't, but I don't think it helps anybody except the one person that got it right, okay? Okay. Now, I mentioned that because, well, you'll see. I'm going to leave it at this on this topic because I want to introduce another one, and we'll work on this one more next time. Okay? Just got to get into vector fields, line integrals, net surface integrals, and the integral forms and all that stuff. And we've only got, well, we've got over a month. But tomorrow's the first of the month. And the fourth of the next month is our last class. Maybe the third. I mean, we figured out the dates. I can do that, but I'm not going to show off. Okay. Now, I want to look at something else, and it's something on the table here that I'll then illustrate on the board. Okay, now in two, like some of you have this and some of you don't, but I'm not seeing many pictures that show exactly what I'm talking about, okay? So I'm going to say that this gremlin is attracted to this planet by vector with a force that's represented by this vector, okay? Now this gremlin is a little further than this gremlin, so its vector is going to be a little shorter. It's going to be back toward the center of the planet. I kind of missed the center, but you get the idea. And this is going to be shorter, and this is going to be even shorter. These are going to be pretty short, and each one is going to be directed toward the planet. So if you drew a picture that looks kind of like this, it would have all the aspects that I think it should have. Now, some of you, I'll just put a few points out here. We're drawing arrows from the center out to the point. Now, if you use the vector definition of Newton's law of universal gravitation, that's your r vector, and you'd multiply by the universal gravitational constant, the product of two masses, divide by the square of the magnitude of the r vector, and then take a unit vector in this direction, and then put a negative sign in front of it. If you've had physics one, you should understand what I just said, okay? But these arrows aren't the arrows I asked for. I asked for the force exerted on each of these little points, and I just said, oh, and that's a bunch of gremlins surrounding the planet. All right. Now, if I want to draw this vector field, without the gremlins, I draw some concentric circles. So this circle is supposed to represent a circle twice the radius of the planet, 3 times, 4 times the radius. Right, twice the radius of the planet, let's just say that our vectors are doing this. They'll all have equal magnitudes, not that I'm doing all that good a job of getting the magnitudes equal, and they'll all point to the center. So there's part of a vector field. Now, has everybody had differential equations? Anybody that hasn't? Okay. Well, you have direction fields and differential equations. If you remember about direction fields, these are kind of similar to direction fields for functions, but they don't have just direction, they have magnitudes. If we go up to twice as far as this one, what should be out to this one, all the vectors would be 1/4 as great because everybody should know that gravity is an inverse square. No, okay. But if the use of similar triangles isn't second nature to you, I'm not sure anybody would have mentioned the idea of an inverse square force, although I kind of expect it probably. Okay. So, I mean, you had their science course, I think, or whatever. So you put a bunch of vectors about 1/4 the length because you're twice as far. The inverse square of 2 is 1/4. Okay. So you're getting a vector field. And then here, well, the vectors are going to be longer than these, shorter than these. So maybe you just take a guess and you do something like this. This would be a vector field with what we call an inward divergence toward this point here. Okay. If this was a positive charge repelling other positive charges, you draw the arrows in the opposite direction. If it was a repulsive force, it'd be pushing things away. You'd have a positive divergence. It's like you have stuff. If this was flow of a fluid, it would be converging toward the center of this planet. Okay. If it was a repulsive force, you'd be using vectors that push away from the planet. It would be diverging from the center of the planets. Okay. There's a term. It's a whole big deal, divergence. This is an example of negative divergence. Okay. Now, let's take another field. I'm going to give you a formula. What symbol do I want to use for the vector field? I'm just going to say F of X, Y. F's got an arrow over it, so it's a vector. It's at point X, Y, so it's a field that covers whatever domain of the XY plane you want to apply it to. F of XY equals YI minus XJ. This is a badly represented unit circle. which means at this point's 1, 0, this point's 0, 1, negative 1, 0, 0, negative 1. If you plug those coordinates in, at this point, y is 0 and x is 1. So it's negative xj. Here, up here, it's y is 1, so it's here. At this point, which is 0, negative 1, it's going to be 0i minus negative 1j, which is going to be okay. I'm using the y's and the x's in these. I mean, at this point, y is, well, I'll write it, yi equals I. Negative xj equals negative j. Xj equals j. And down here, negative y I equals negative I. You notice that these vectors are all pointing tangent to the circle in such a way that they were forces, they'd be rotating the circle around here, okay? Also at points inside the circle, this would be one over square root of 2i minus j. Be a unit vector, it'd be tangent to the circle. So you have these unit vectors tangent to the circle all the way around. Does that make sense? This is a circulating field. Okay, we're officially out of time. I'm going to hold you for about another minute. Take careful note of this. Divergence is del dot F. Curl is del cross F. Okay? Which one of these fields seems to be curling? Well, this field's kind of curling around the origin, isn't it? So this field is going to have significant curl. And it's going to have no divergence. Nothing is diverging away from the origin. Okay? If I take this and do divergence of F, it's a partial respect to x of y plus a partial respect to y of x, which is 0. Now, you hopefully remember the del operator, partial respect to x times I plus partial respect to y times j, and then with k also if you have 3 dimensions, okay? This all works in any number of dimensions. Well, no, up to 3 dimensions, okay? So this field has no divergence. Now, I don't have time to write out an expression for this field, okay? But it'd be easy to write out. And we'd find that this field has no curl. And divergence and curl and the way they behave in mechanical and electromagnetic systems and so forth is really, really, really important stuff. Okay? So you won't see divergence and curl until text assignments from next week. That's what I'm going to give you as an introduction to vector fields. So you ought to try to get into section 1 of chapter we on, that'd be chapter 6, I think. Okay. So do a little reading, try to familiarize yourself with the concepts, and we'll try to make it more specific. And, think about similar tribes.